When you're first taught about balancing equations, the focus is usually on making sure you have the same number of each atom on each side of the equation. But you also need to make sure that the net charge is the same on both sides as well. Take this reaction between copper and silver ion, for example. There's one copper and one silver on each side, but the total charge on the left is +1, and on the right is +2. That means we've lost an electron during this reaction. It may only be one electron, but it's still breaking the law of conservation of mass. We can get a better sense of how to fix this by breaking the reaction into two halves. In the copper half, copper is losing 2 electrons, but in the other half, silver ion only needs 1 electron to form silver metal. So we must need 2 silver ions for every 1 copper 2 that's forming. When we add the two halves back together, we get an equation that's now both atom balanced and charge balanced. Reactions like that aren't too bad, but when you have a redox reaction in acidic or basic solution, things can be a little more confusing. But fortunately, there's a stepwise approach you can take to make things a little easier. Let's start with the following reaction, which is clearly not balanced. And for this example, let's assume the reaction is an acidic solution. The first thing we'll do is split the reaction into two halves, like we did earlier. Next, we're going to atom balance each half. The zinc half is already balanced, with 1 on each side, but the vanadium half is missing 2 oxygens on the product side. For acidic solutions, you can use hydrogen ion and water as needed to atom balance one or both halves. If it's basic, well, we'll talk about that in a minute. For most acidic half reactions like vanadiums, you'll balance the oxygens by adding the appropriate number of waters on the other side. This is going to introduce some hydrogens, but we can balance those using H+. At this point you might be thinking, why is it okay to add H+ in water from seemingly out of nowhere? But if it's acidic and aqueous, there is H+ in water present in solution. So we're not adding anything that's not already there. Okay, technically it's hydronium and not H+, but using hydronium would make balancing a lot more difficult. So we use H+ for the sake of convenience. Once you're atom balanced, you'll want to charge balance each half using electrons, like we did earlier with the copper and silver example. For the zinc half, we can add 2 electrons on the right side so that both sides have a total charge of 0. With the vanadium half, the total charge is +5 on the left and +2 on the right. So if we add 3 electrons to the left side, that'll bring its net charge down to +2. Now we'll do what I like to call electron balancing, which means we'll modify one or both halves so they're both showing the same number of electrons. In this example, the zinc half is losing 2 electrons while the vanadium half is gaining 3. So if we multiply the top half by 3 and the bottom half by 2, that'll give us 6 electrons in each half. Finally, it's time to add the two halves back together. Doing that here gives us a reaction that's both atom balanced and charge balanced. Now let's go back and assume the reaction is in basic solution. There are different ways to tackle basic reactions, but what I like to do is to start by pretending it's acidic. That way the balancing steps are the same regardless of which type you have. You just have to do an extra step to convert the equation to a basic one. And the way we'll do that is by adding this equation in a way that removes H+ from the redox reaction. Just like back in step 2, we're not adding anything that isn't actually there. This is the autoionization of water, which you were probably taught earlier in a discussion about pH, though you may have seen it written this way using hydronium instead of H+. Since H+ is on the left side of our redox reaction, we'll add the equation as it was given. Hypothetically, if the hydrogen ions were on the product side, we would have had to flip the equation around. And since we have 8 hydrogen ions in our redox reaction, we'll have to multiply the autoionization equation by 8. When we add the two equations together, the hydrogen ions drop out, giving us this equation, which we can simplify a bit by subtracting 4 waters from each side. The resulting equation is still both atom balanced and charge balanced, only now it's correctly showing a basic solution.